Hi, welcome back to the Power DSP lessons. In this episode, we are going to see an example to understand how to derive the discrete and signal from an analog signal and how to reconstruct back the analog signal from the discrete signal for a given sampling frequency. Let's get started. This is our example. There are three frequency components in this analog signal. We need to find out the Nyquist frequency followed by the discrete time signal that we get after sampling with the sampling rate of 5 kHz, and then finally the analog signal that we reconstruct with the same sampling rate. Let's move to the case A first. In this case, we have to find out the Nyquist frequency. We have already seen how to find the Nyquist frequency. The first step is to find the maximum frequency component in the signal and then multiply that by 2 will give the Nyquist frequency. After converting the signal into the standard form, we get three frequencies in which F3 is the maximum frequency component. Nyquist frequency is 2 into 6000 Hz is equal to 12 kHz. In case B, we have to find the discrete signal after sampling. Here the sampling frequency is 5 kHz. The first thing we have to do here is to convert the analog signal to digital by replacing T to NTS, and then we substitute TS is equal to 1 by Fs. After substituting, we get X of n like this. We can simplify it further as shown in the next slide. We can rewrite the terms 3 by 5 as 1 minus 2 by 5 and 6 by 5 as 1 plus 1 by 5 in order to simplify it further. Next, we have to multiply 2 pi n inside in these terms. Then we can simplify these two terms. Since sin 2 pi n minus theta is equal to minus sin theta, we can replace the term 3 sin 2 pi n minus 2 pi 2 by 5 n as minus 3 sin 2 pi 2 by 5 n. Similarly, cos 2 pi n plus theta is equal to cos theta. We can write the term 10 cos 2 pi n plus 2 pi 1 by 5 n as 10 cos 2 pi 1 by 5 n. We can simplify it further by adding these two terms, and then we get X of n is equal to 15 cos 2 pi 1 by 5 n minus 3 sin 2 pi 2 by 5 n. Here we have to notice one important thing, that we have started with 3 components but ended up with 2 components. What happened here? We see that in the next slide. So before ADC, the analog signal has 3 frequency components. Then after converting it to the digital, there are only 2 components. What happened here? Aliasing. Since we haven't chosen the correct sampling frequency, we have ended up with aliasing. Here the maximum frequency component is 6 kHz. So we must have chosen the sampling frequency of 12 kHz and above. But the sampling frequency Fs here is 5 kHz. With this, we can accommodate frequency components up to Fs by 2, that is 2.5 kHz only. The frequency components above this 2.5 kHz are going to alias. In our example, we have 2 components above 2.5 kHz. The first one is 3 kHz and the second one is 6 kHz. And these 2 components are going to alias. We can visualize this aliasing in this picture. We have to draw a straight line to meet the corresponding slanting edges to find the aliases. Here 3 kHz is aliased with minus 2 kHz and 6 kHz is aliased with 1 kHz. We can recheck this by feeding the values in the expression Fi plus Kfs. By substituting k is equal to minus 1, we are getting the same results here. Okay. Next, we will see how to reconstruct the analog signal from this discrete signal. Here we can equate the 2 pi 1 by 5 n to the standard discrete form of 2 pi fnts. We get the value of f0 as 1 kHz after solving the equation. Similarly, we get 2 kHz by comparing the second term with the standard form. Finally, we get the analog signal by substituting these 1 kHz and 2 kHz in the standard analog form of 2 pi ft. Okay guys, this is P Madhan Mohan for Power DSP lessons. Bye bye.